something is amiss in our comprehension of the universe. Cosmology is, by all accounts, heading for a standoff on one of its most essential inquiries. How fast is the universe growing? For more than a decade, two sorts of estimations have been in conflict. Perceptions of the current universe ordinarily track down the rate of development, called the Hubble constant, to be around 9% quicker than expectations based on early universe data. Scientists had hoped that the James Webb Space Telescope, the most high-level telescope ever constructed, would assist with settling the inquiry. However, it has thus far failed to provide a resolution. Instead, the preeminent observatory has solidified the error with amazingly exact new observations that threaten to overturn the standard model of cosmology. The new physics expected to alter or even replace the 40-year-old hypothesis is now a subject of debate. An astonishing and fascinating possibility is that there's something we fail to understand about the universe. Join us as we delve into new ultra-deep images from James Webb. Recently, it has been confirmed that something is truly amiss with our understanding of the universe. Our universe began with a bang, the Big Bang, where energy, mass, and space sprang into existence all within a fleeting moment. Then, the young universe was formed, an expanding roiling plasma stock of matter and antimatter particles that popped into reality only to annihilate each other upon contact. Left to their own devices, the matter and antimatter within this plasma should have consumed each other completely. However, scientists believe that some unknown asymmetry allowed more matter than antimatter to be produced, preventing the universe from immediate implosion. Gravity compacted the plasma pockets, pressing and heating the matter so that sound waves traveling just over around 50% of the speed of light, called baryon acoustic oscillations, undulated across their surface. In the meantime, the high-energy density of the early universe's compacted contents expanded spacetime, pulling a small part of this mass safely from the sphere. As the universe expanded like a bubble, the standard story goes, normal matter, which interacts with light, coagulated around clusters of invisible dark matter to form the first galaxies, connected together by a vast cosmic web. At first, as the universe's contents spread out, its energy density and thus its expansion rate decreased. However, approximately 5 billion years ago, galaxies began to retreat once more at a consistently faster rate. The reason was another invisible and mysterious element known as dark energy. The simplest and most popular explanation for dark energy is that it is a cosmological constant, an inflationary energy that is the same everywhere and at every moment, woven into the expanding fabric of spacetime. Einstein named it lambda in his theory of general relativity. As our universe evolved, its overall matter density dropped while the dark energy density remained the same, increasingly making the latter the major contributor to its overall expansion. Added together, the energy densities of standard matter, and dark energy set forth the upper speed limit of the universe's expansion. They are also key ingredients in the lambda-cold dark matter, lambda CDM model of cosmology, which maps the evolution of the universe and predicts its end with matter eventually spread so far it encounters a power death called the Big Freeze. Many of the model's predictions have been shown to be highly accurate, but here's where the problems start. Despite much looking, astronomers do not know what dark matter or dark energy are. As Ofer Lahav, a professor of cosmology at University College London who is involved in galaxy studies of dark energy, said, most people agree that the universe's current composition is 5% ordinary nuclear matter, 25% cold dark matter, and 70% dark energy. The embarrassing truth is that we don't understand the last two of them. But an even greater threat to the lambda CDM model has appeared. Depending on the method astrophysicists use, the universe appears to be expanding at different rates, a discrepancy known as the Hubble tension. Techniques that peer into the early universe show it expanding significantly faster than lambda CDM predicts. Those methods have been scrutinized and confirmed by countless observations. As Nobel Prize-winning astrophysicist Adam Rees, who led the team that made the new James Webb measurement, said, "The only reason that I can understand at this point for them to differ is that the model that we have between them is perhaps missing something. Measuring the universe's expansion takes a bit more than a radar gun. The main method to measure this expansion looks at the so-called cosmic microwave background, CMB, a remnant of the universe's first light produced just 380,000 years after the Big Bang. The imprint should be visible across the entire sky, and it was planned to find a Hubble constant with less than 1% uncertainty by the European Space Agency's Planck satellite between 2009 and 2013. In this cosmological image, the universe is generally uniform, but hotter and colder patches, where matter is more or less dense, reveal where baryon acoustic oscillations made it bunch as the universe exploded outward. This soap bubble structure expanded into the cosmic web, a network of tangled strands along whose intersections galaxies would be born. By studying these swells with the Planck satellite, cosmologists inferred the amounts of standard matter and dark matter and a value for the cosmological constant or dark energy. Plugging these into the standard model spat out a Hubble constant of about 67 kilometers per second per megaparsec. We should pause on this number for a second. If a galaxy is a distance of 1 megaparsec away from us, then that would mean it will recede from us at 67 kilometers per second. At 20 megaparsecs, this recession grows to 1,340 kilometers per second and continues to grow dramatically from there. If a galaxy is any further than 4,175 megaparsecs away, it will recede from us quicker than the speed of light. A second method to find this expansion rate uses pulsating stars called Cepheid variables, stars with helium gas outer layers that expand and contract as they absorb and emit the star's radiation, making them periodically flash like distant signal lights. In 1912, astronomer Henrietta Swan Leavitt found that the brighter a Cepheid variable was, the slower it would flash, enabling cosmologists to measure a star's absolute brightness and thereby its distance. It was a milestone discovery that turned Cepheids into abundant standard candles to measure the universe's large scale. By hanging observations of pulsating Cepheids together, cosmologists can build cosmic distance ladders, with each rung taking them a step back into the past. It is one of the most reliable means that astronomers have today for measuring distances. To build a distance ladder, astronomers construct the first rung by picking nearby Cepheids and cross-checking their distance based on pulsating light with that found by mathematics. The next rungs are added using Cepheid readings alone. Then astronomers look at the distances of the stars and supernovae on each rung and examine how much their light has been redshifted to longer, redder frequencies as the universe expands. This gives an accurate measurement of the Hubble constant. In 2019, the method was used by Rees and his colleagues, who trained the Hubble Space Telescope on one of the Milky Way's closest neighbors, the Large Magellanic Cloud. Their result was significantly higher, showing a growth rate of 74 kilometers per second per megaparsec compared to the Planck measurement. However, Hubble, lacking fundamental accuracy for the crowded regions of space the team was focusing on, caused some distant Cepheids to blur into adjacent stars. Disagreeing cosmologists had some room left to argue that the result, however stunning, might have come from a measurement error. So, when James Webb launched in December 2021, it was poised to either resolve the discrepancy or cement it. At 6.5 meters, Webb's mirror is just over twice the size of Hubble's, which is just 2.4 meters wide. Not only can James Webb detect objects 10 times fainter than Hubble can, but it is also much more sensitive in the infrared range, enabling it to see in a broader range of frequencies. By comparing stars measured by James Webb in the galaxy NGC 4258 with type Ia supernovae, another standard candle since they all burst at the same absolute luminosity, in distant galaxies, Rees and his colleagues arrived at an almost identical result, 73 kilometers per second per megaparsec. Other measurements, including one made by Fredman with the Hubble Space Telescope on the fast brightening of the brightest tip of the branch red giant stars, and another with light bent by the gravity of massive galaxies, returned specific results of 69.6 and 66.6 kilometers per second per megaparsec. A separate result using the bending of light also gave a value of 73 kilometers per second per megaparsec. Cosmologists were left reeling. According to Ryan Key, a cosmologist at the University of California, Merced, who has been working to figure out the Hubble tension, the CMB temperature is measured at the level of 1% accuracy, and the Cepheid distance ladder estimation is approaching 1%, so a difference of 7 kilometers per second, even though it's not large, is very unlikely to be a random chance. There is something distinct to figure out. The new result leaves the answer wide open, dividing cosmologists into camps pursuing vastly different solutions. Following the Hubble Space Telescope result, an official attempt to resolve the issue at a 2019 conference at the Kavli Institute for Theoretical Physics in California only caused more frustration. As the late Vera Rubin, who found evidence for dark matter, said at the time, "No one wanted to give up their toy. Everyone involved believed so strongly in their own results and in the way their observations and measurements were done correctly. It just left people wanting to figure out how to resolve this." In February 2023, with James Webb and another independent Hubble Distance Ladder result confirming the Hubble tension, cosmologists are left with three potential explanations: measurement errors, new physics, or some combination of the two. Most of the data supports new physics. The simplest and most popular theory is that dark energy acts differently today than it did in the early universe. If dark energy was strong at one time and then faded away, it would make the universe look smaller when we look back to the early universe, making the expansion rate appear faster. There are other explanations, such as the possibility that there are two types of dark energy or that dark matter interacts with light, but these explanations present complications that cosmologists are wary of. Without further data, dark energy and dark matter aren't the only secrets James Webb is helping to solve. When it launched, it was tasked with looking further back in time than any telescope before it. James Webb's revolutionary new imaging technology enabled it to see galaxies formed just 300 million years after the Big Bang. However, while examining the universe's origin, cosmologists noticed that these early galaxies are much more massive and evolved than the standard model predicts. Early galaxies should have been full of young, hot stars forming at a very fast rate, but James Webb showed many of them were overflowing with heavy elements from earlier generations of stars and actively growing bulging centers of supermassive black holes. Let's break down this fascinating topic further. 1. The fundamentals of cosmology, the Big Bang and early universe. The universe began around 13.8 billion years ago in a hot, dense state. Soon after the Big Bang, it expanded rapidly, leading to the universe we observe today. 2. Measuring the expansion rate. Early universe measurements using the cosmic microwave background, CMB, provides one method for measuring the universe's expansion rate. Current universe measurements, observing pulsating stars, Cepheid variables, and type Ia supernovae, offer another method, yielding a higher growth rate than expected by early universe measurements. 3. The Hubble tension. This discrepancy between early and current universe measurements suggests potential errors or the need for new physics. 4. James Webb Space Telescope capabilities. With unparalleled precision and sensitivity, James Webb confirms the higher growth rate seen with current universe measurements, validating existing inconsistencies and prompting a reevaluation of cosmological models for potential explanations. Measurement errors, new physics, or some combination of the two. 5. Implications for cosmology, a threat to the standard model. The persistence of the Hubble tension suggests weaknesses in the lambda CDM model, prompting the need for revisions. Resolving the tension requires advancements in how we interpret cosmology, which relies on future observations and theoretical developments. 6. Early galaxies and discoveries, unexpected characteristics. James Webb's observations reveal early galaxies with surprising properties, challenging existing models of galaxy evolution. In conclusion, James Webb's precise data intensifies debates in cosmology, requiring further investigation and possibly redefining how we interpret the universe. Exploring these topics opens new frontiers in astronomy, inviting deeper insights into the nature and evolution of the universe.